Hello and good morning. My name is Madelyn McClure, and I'm here to talk to you today about quantifying impact resistance, an experimental analysis of force distribution on equestrian helmets under simulated weight drop conditions. A little bit about me. I'm 15 years old, I'm from the EPA region, and I call Endless Mountains Pony Club home. I'm a D3 in dressage and a D3 in horse management. Here's the flowchart that I've used to outline my project. I started with a problem. There's a variety of helmets on the market ranging from $40 to $700, leading many equestrians to struggle trying to choose a helmet. So my question is, assuming that all helmets meet ASTM and SEI standards, which helmets are the most effective at reducing simulated force of impact in various locations of the helmet? Research. Horseback riding is the leading cause of sports-related head injuries. Approximately 20% of all equestrian injuries involve the head, making head trauma the leading cause of death in equestrian activities. Wearing a properly certified helmet can reduce the risk of severe head injury by 70 to 80%, according to safety studies. In 1980, the United States Pony Club began to independently track equestrian accidents and develop their own helmet safety standards. In 1990, ASTM published its first standard for riding helmet safety. Today, ASTM and SEI standards testing includes impact attenuation tests, penetration tests, retention system tests, shell deformity tests, and helmet stability tests. So what is ASTM? It's a global standards organization that develops and publishes technical standards for various products, materials, and systems. ASTM has a specific standards for equestrian helmets that outlines rigorous testing criteria for impact, resistance, and retention system. Helmets are subjected to simulated impact scenarios to ensure they protect riders in real-world falls or accidents. SEI, what is it? An independent third-party certification body that tests products to ensure they comply with ASTM standards and other safety requirements. SEI certified equestrian helmets that meet the ASTM standard verify their safety and reliability through consistent testing. Helmets that pass the SEI certification carry the SEI label, indicating that they met the ASTM standard and have been tested by an accredited lab. The MIPS helmet. When you hit your head in a fall, it often creates a rotational motion in your brain. This then causes brain injury. Well, MIPS low friction layer allows the head to move 10 to 15 millimeters in all directions inside the helmet, which reduces the rotational motion to the brain. With this research in mind, I will hypothesize that the 1K MIPS helmet will protect against force throughout the helmet more effectively than others when force is directly applied to the top of the helmet. Materials. I used a mannequin head, a Vernier Logger Pro low force accelerometer sensor, a Vernier Logger Pro force interface, a laptop, 3 helmets including an Ovation, a GPA, and a 1K with MIPS technology. I also used weights and lastly a measuring tape. My variables: the independent variable, the helmet type; the dependent variable, the force applied to the mannequin head. Control variables: location of the impact, the height from which the mass was dropped, and the amount of mass dropped. My procedure: first, I obtained all my materials. Then I placed the low G accelerometer sensor in the spot of the helmet being tested. I ensure that it is secure by taping it down, whether this is the top, front, back, left, or right. Then I place the helmet on the mannequin head and secure the straps. I place the helmet 35 centimeters underneath the 500 grams of mass. Drop 500 grams of mass directly onto the top of the helmet using the X to ensure proper drop location. Repeat for 3 trials for each location. Record the force applied using the Logger Pro interface. Move the sensor to the next location, calibrate the sensor, and repeat. Here you can see a picture of my process. You can see the 1K helmet on top of the mannequin head. Here the Logger Pro is on the left side of the helmet where it will be tested. Here's a picture of the low G accelerometer close up, and here it is inside the helmet. You can see that it's quite small and will not impact the fit of the helmet. Here's an equation that assumes that a 68-kilogram rider falls off of an average-sized horse without a helmet. The average threshold for concussion is 600 to 700 meters per second squared, with anything higher resulting in traumatic brain injury. The GPA helmet. Here we can see that the highest is the top in the middle. While our other numbers are quite low, it's lowest in the right and the left side. The ovation helmet. Again, quite high in the top and quite high in the back as well. Pretty low in the front and in the middle, in the right and left. The 1K with MIPS technology is quite consistent across the board. We can see that the highest is the right side, with the left and the top middle pretty close behind. This is easier seen in graphical format. Here we can see that the GPA is quite high at the top, but pretty low across all of their standards. We can see that the ovation is the highest at the top as well as the back, and about average on the right and left side. We can see that the 1K is very consistent across the board. Analysis. The GPA and ovation helmet both performed similarly when force was applied through the top of the sensor. However, the GPA helmet had less of an impact of force when the sensor was placed in the back, right, and left of the helmet compared to the ovation helmet. This seemed to correlate with the helmet fit of the mannequin. The GPA helmet wrapped around the back of the mannequin head and buckled more securely than the ovation helmet did. This may have led to the force measured in those locations. The overall trend to the MIPS 1K helmet is much lower across the areas where force was measured compared to the other brands of helmets. The MIPS force was measured compared to the other brands of helmets. The MIPS technology that addresses rotational falls may have decreased the realized force in various locations of the helmet when the force was applied to the top of the helmet. Why is this significant? The frontal lobe. A fall or blow to the frontal lobe of the head can cause damage, potentially leading to impaired judgment, changes in personality, difficulty with voluntary motor skills, and emotional dysregulation. In this study, the GPA helmet would have damaged the frontal lobe the most. Then we move to the parietal lobe. Trauma to the top or side of the head can affect the parietal lobe, leading to difficulty with spatial orientation, numbness, and impaired coordination. Again, we see the GPA with the most. Then we move to the temporal lobe. A lateral impact can damage this lobe, possibly resulting in memory loss, impaired hearing, and problems understanding language. In this study, the ovation helmet would have damaged the temporal lobe the most. This is most likely due to the fact that the ovation helmet does not wrap all the way around the rider's head. The occipital lobe. A fall that impacts the back of the head can cause damage to this lobe, leading to visual disturbances, difficulty recognizing objects, and problems with visual spatial processing. Again, we see the ovation leading by far. The cerebellum. Trauma to the back or base of the skull can affect the cerebellum, causing loss of balance, dizziness, and difficulty with fine motor tasks. In this study, the ovation helmet would have again damaged the cerebellum the most by a large margin. And lastly, the brainstem. Severe trauma to the base of the skull can damage the brainstem, potentially causing loss of consciousness, difficulty breathing, and severe motor impairment. While data was not collected directly on the brainstem area, it's still important to include the consequences of a damaged brainstem. The United States Pony Club Safety Handbook describes regulations for proper helmet fit and standards in Appendix A. Although all helmets tested were ASTM and SEI approved, the fit of the actual helmet impacted the protection that it provided. A recommendation from this study is that helmets be properly fitted by a professional or Pony Club official. To conclude, I now accept my hypothesis that the 1K MIPS helmet will protect against force throughout the helmet more effectively than others when force is directly applied to the top of the helmet. Some faults of this experiment may include: the sensor was not perfectly centered in the helmet. Mass was not dropped directly on the middle of the helmet at times. The helmet was not properly fitted to the mannequin head, and not all helmets were produced at the same time. To further my research, I'd like to simulate continuous damage to a helmet to determine how it deteriorates, showing how a fall may affect helmet performance. I'd like to use other safety equipment, such as safety vests, to determine how force is applied during a fall. I'd like to determine how the age of a helmet could affect its structural integrity, even if it doesn't sustain a fall. Here are my references. I'd like to thank you for your time. Now I will take any questions.